guys, now we will start with the concept, which is the last concept in this topic, which is about the standing waves. Standing what? Waves. Now I will show you what do I mean by standing waves.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
Okay, guys. This is a demonstration for standing waves. If you see here, we had a generator, right? Wave generator produces that produces disturbance or oscillation. Here we observe that something called standing waves, guys. If you look to this high-speed camera, this is why it's called standing waves, because the disturbance does not transfer through. Okay, and only each particle will oscillate in its position, right? With disturbance does not move. All of the string is disturbed at the same moment. I can compare it with progressive waves. Okay, guys, look to this. This is a progressive wave. Progressive waves, guys, look, a disturbance will travel from one particle to another, right? From one particle where to another. Here there's a transfer of energy or transfer of the disturbance. Here I want to show you two different things. First of all, guys, here all the particles have the same amplitude. All the particles have the same what? Amplitude. Here, guys, all the particles in progressive waves, look, all the particles will oscillate between this position and this position. So all of them will have the same amplitude. All of them will have the same amplitude. They will have different phase, right? The phase here is different than the phase here, different than the phase here, different than the phase here. Also, guys, the disturbance travels. If I compare it with the standing waves, if you look here, let's say this is the equilibrium position. Guys, pay attention here. The particle here is different than here, is different than here, is different than here. Look, they will have different amplitudes, right? They will have different what? Amplitude. In standing waves, guys, in standing waves, the particles will have different amplitudes, but in progressive waves, they have the same amplitude. All the waves have the same amplitude. Look, all the particles, yani eventually the maximum displacement for all of them will be the same. Yani this particle eventually will have this amplitude at certain moment, or maximum displacement. This also, this and so on. The second difference, guys, حكينا إنه هون there's no transfer of energy or there's no transfer of disturbance. The waves just oscillate up and down as what we see in the video or in this high-speed camera, right? This point does not even have to oscillate. This is why it's called standing waves, because it's oscillating or there is no disturbance or there is no movement of the disturbance. They just oscillate up and down. The other important thing, guys, this is called later, we will see this is called antinode. Sorry, node. This is node. This is what also is called node. Between nodes, guys, all the particles oscillate in phase. Between any two successive nodes, all the particles oscillate in phase. What does this mean? Either all the particles are oscillating or are moving up, or all the particles are moving down. So this is the second difference. Look, all the particles either moving up or down.
So here we have what's called the second harmonic.
Okay, guys, is that clear? This is called node, and this is called what? Node. Between nodes, all the particles oscillate in phase. Yani either all the particles are moving up or all the particles are moving down. Okay? Any question about that? So here, guys, the main difference, I will stop here. The main difference between progressive and stationary. In stationary or standing waves, no net transfer of energy. Here the wave is move. Yani there's a transfer of energy. The amplitude varies from 0 at nodes or maximum at antinodes. Yani the amplitude of the particles will vary. Here all the particles will have the same amplitude. Same amplitude, guys, means same maximum displacement. Frequency, all of them, they have the same frequency. Wavelength, we'll talk about it later. Phase difference, this is what I discussed with you this class. And with phase difference, for stationary waves between nodes, all particles are at the same phase. Here, any two particles have a phase difference. Later, we will discuss how can we find the phase difference in standing waves. How can we find, or we already discussed that, how can we find the phase difference in progressive waves? Okay, guys? Talked about what? Standing waves, or we started with standing wave. We introduced something called what? Standing waves. From its name, it's called standing, means there is no transfer of energy. There is no transfer of energy, or sometimes they are called stationary waves. I will explain now for you what is meant by standing waves.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if a frequency generator is connected to what's called a wave driver, it's just a speaker. It's going to pump up and down.
Listen, guys, please. Guys, please watch this video carefully because I will ask you several questions. Okay, please, I will ask randomly several questions about this video about the standing wave. Is the sound of the YouTube clear?
واضح أستاذ.
Okay, yeah. Pay attention, please.
Down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump rope. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was that around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths.
Okay, guys. Anyway, guys, this is called what? Standing wave, right? This is called what? Standing waves. It's called standing, or they are called standing waves because, guys, there's no transfer of the disturbance does not transfer amplitude like what we see in the previous time. This is, let's say, in the speed hike or in high speed camera standing wave. Guys, standing wave just oscillate up and down. يعني oscillation or disturbance up and down. In progressive waves like this one, look, there's a movement. يعني disturbance moves from left where to right. It's very obvious, right? The disturbance moves from left to right. Beside that, guys, here each particle has a certain amplitude. يعني this particle here, this is the amplitude of each particle. Because the particles here either oscillate in this way or oscillate in this way. This is what I observed, right? And with the time, the particle, this is the maximum. Let's say this is, let's consider this particle. This particle will oscillate only between these two positions only. This particle oscillates only between these two positions, and so on. So they have, each one has certain amplitude. Is that clear? Okay, guys. Muhammad Tahir. What are these points called from the video?
Nodes.
Nodes, right. Okay. These points are called what? Nodes. Guys, those nodes, they don't oscillate. صح? Did you see that in the video? They will not oscillate. They will stay in their position. They will not oscillate at all. Okay, type. This point, which has the maximum amplitude, what is it called? هلا هاي البوينت جايز وهاي البوينت اللي فيها maximum amplitude هدول بنسميهم احنا anti nodes. هلا main thing that I want you to observe from the video هو pattern تاع standing waves. انه the standing waves, this is what did we see, right? صح ولا لا؟ progressive لا عادي, we can observe wave, regular wave, like the video, like the simulation that we watched here, right? تمام عادي, wave. Here لا, standing waves I will observe like something like this. progressive هيك عادي. This is what I will observe. Okay, طيب بس هلا I'm talking about the differences. ركزوا معي. اتفقنا انه بالبروجريسيف في speed وفي movement وهاي. stationary ما في transfer of energy او no need to transfer from one point to another. الامبليتيود حكينا بالstationary or standing waves varies from 0 at nodes to maximum at anti-nodes. It's the same for all particles. Frequency, they have all the particles oscillate at the same frequency. All the particles oscillate at the same frequency except mean those at nodes, because they did not oscillate أصلا. The particles at node, they did not oscillate. If you observe that, he put his finger على البوينت أو النود, صح؟ nothing ايش changes. هلا ممكن أشوف هيك. If you remember, we observed something like this, صح? oscillates up and down, right? وشفنا مثلا أكثر من هاي. طيب هلا المين بوينت تحتي guys هاي الphase difference between nodes, guys. يعني if I consider the particles here between this node okay Rand, and this node, if I consider these nodes, guys, all the particles are in phase. Why all the particles are in phase? Because either all the particles move up or all the particles move down. And between two successive nodes, all the particles will oscillate at the same phase. عشان هيك they are in phase. All the particles between successive nodes, they are in phase. With progressive, previously, guys, we learned how to find the phase difference between any 2 points by considering the time shift or position shift divided by, if you remember, divided by lambda times 360, or by finding the time shift divided by period times 360. This is the phase difference that will be that was found for progressive waves. And how does stationary waves produced? Stationary waves, guys, may be set up when a progressive or progress waves reflected back from a surface, and these waves interfere with the progress waves still traveling in the original direction with the same frequency and what amplitude. If I consider this, if I go back to the video,
they're not exhibiting consistently constructive or destructive interference at any one point. If I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example,
okay, guys. In order to understand how does standing waves, or how do standing waves, or how can the standing waves be formed? Look here, please. Here, guys, we have outgoing waves. Okay? Is that clear? From this point, here we have outgoing waves. Here we have reflected waves. Pay attention, guys, to this, because you will be asked about that. Okay? We have outgoing waves from the generator. Wave generator. We have reflected waves from this fixed end. As a result of that, guys, they will interfere. These waves will interfere. Here, guys, at the position of antinode, they interfere constructively. Always. All the waves, all the incoming waves or outgoing waves and reflected waves meet at this position constructively. Okay, so here they are exhibiting antiphase. Just 1 second. At this moment, sorry, they are exhibiting a constructive interference. So here we have antinode. Here, guys, the outgoing waves and the reflected waves always interfere destructively. Guys, when they feel destructively, you know that the amplitude will be cancelled out, right? The amplitude will be cancelled out. They have the same amplitude, they have the same what? Frequency. Okay, guys? احنا بنقول if they meet constructively, يعني here outgoing wave, let's say crest, will reflected wave also crest. Here, they will meet in this way. You have always several of outgoing waves or several of reflected waves, right? They will meet here.
Mm.
The outgoing waves or reflected waves meet in phase, crest with the crest, وhere they meet as anti-phase. So crest with the trough. And here in phase, وhere what? Anti-phase. Okay? So they
Okay.
form this shape of the wave, which is called standing waves. Any question, guys? Because you'll be asked about these things. Also, we have another question here, guys, according to this video. Can the standing waves be formed at any frequency? He started varying the frequency, but at
مظبوط
specific frequencies only. حتى he mentioned that. Like if I double this,
مظبوط
I will
بالظبط
get a second harmonic. هلا between the first مثلا to reach مثلا second harmonic or third harmonic or sixth harmonic, like what he did in the video, there is a disturbance, but there is no wave pattern. يعني we observe that the string is oscillating, right? Oscillating, but we did not observe we did not observe a pattern of the standing wave. Did you observe that or not? Here, guys. This is called second harmonic. I will explain that later. But this is called what? Second harmonic.
I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up. Possibility for a standing wave for a string that's held at both ends. Because notice this is a node in the middle.
Guys, pay attention now. He will vary the frequency. Look what will happen to the string.
So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. First one will be half this number, so 8.5. And there we go.
This is called first harmonic, guys. This is called what? First harmonic.
It's basically the scenario of a jump. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5.
Guys, look here. Here we don't observe any standing waves. We just observed here a disturbance in the string, and the string just oscillate. We did not observe any. This is not a harmonic frequency. Yani the frequency now that he adjusted here, it's not a harmonic frequency for this string. And if you continue changing the frequency, look.
And there we go.
Guys, at specific frequency here, or specific frequencies, we got something called harmonic frequencies. This is called third harmonic. This is called what? Third harmonic. So the standing waves, guys, standing waves, I'll explain that for you. The standing waves, guys, are taking place at specific frequencies. These frequencies are called harmonics or harmonic frequencies. Why there is a specific, or why there are a specific frequencies that the standing waves are formed? Because, guys, look, at these frequencies, all the waves meet here in phase, antiphase, sorry. All the waves meet here antiphase. Or all the waves meet here at antiphase, antinode, meet in phase. Okay? At these frequencies, all the outgoing waves and reflected waves meet in phase at the position of antinode. They meet antiphase at the position of what? Of node. بس at these frequencies. at the frequencies between these harmonic frequencies and at any other frequency, guys, the waves will meet constructively, or they interfere constructively and destructively at any point. يعني بصير عندنا random interference along the string. Random interference means what? At each position we may have constructive interference, then the second moment destructive interference, and so on. So we did not observe a pattern of the standing waves. We have two conditions for the standing waves to take place. First of all, waves must be traveling at the same speed in opposite direction. You have to write this. Overlap, and they should have the same frequency or same wavelength, and same amplitude as well. Right? They must have same amplitude in order to have complete what? Cancellation at the point of node. Okay? We discussed that also. Explain the standing waves. So first of all, رح نحكي عن standing waves in a string, then we will talk about the standing waves in air. Here, to have a standing waves, we must have a taut string that is attached to two fixed points, like what did we see in the video, or what did we observe? When outgoing wave traveling along the string in forward direction, it's reflected back when it reaches the second fixed end with the same frequency, amplitude, but antiphase. Then it interferes with another outgoing progressive wave that is moving in the opposite direction, either constructively, so their displacement add up, or destructively, so their displacement cancel out, creating a new pulse shape. Changing frequency will change what? The wave pattern. Will change the wave pattern.
Hello, in this short video, I'll be introducing standing waves. Let's begin with the simulation of a string that is fixed at two ends. I'm going to send a single pulsed wave along the string, and we'll watch as it reflects off the opposite end.
This is outgoing wave. Okay, Tariq. Now this outgoing wave, when it reaches the second fixed point, what will happen to it? Reflected back. Okay. Answer.
Now watch what happens if I send a second pulse along the wave sometime after the first. Standing waves. Let's begin with the simulation of a... Now watch what happens if I send a second pulse along the wave sometime after the first.
Here, guys, now we have outgoing waves. After that, also we have outgoing waves. We have reflected waves. Look here, guys.
When the two waves meet, they superpose. At some points they will interfere constructively, and at other points they will interfere destructively. This is perhaps best illustrated by sending a progressive wave along our string and watching it reflect off the end. Note that when it does reflect off the end, the two waves one travelling to the left and one travelling to the right, superpose such that certain points along the wave are stationary, they're not moving up or down. We can call these points.
Okay, guys, here, look to the previous one was only single pulses. But actually, we don't have a single pulse. Sorry, not single pulse, a single pulse. Here we will have a continuous generating of the waves, like this. Before the waves reaching the second fixed point, we will have progressive waves, and we will observe progressive waves. Look,
illustrated by sending a progressive wave.
This is a progressive waves. It's like or this wave like the waves that we regularly observed. Now look what will happen to when these waves reach the second fixed position, or second fixed point.
Along our string and watching it reflect off the end. Note that when it does reflect off the end, the two waves, one travelling to the left and one travelling to the right, superpose such that certain points.
Guys, it's obvious here in the waves. We can, let's say, it seems that there are no transfer of the disturbance. The waves are stay in their positions.
Along the wave are stationary, they're not moving up or down. We can call these points nodes. At other points along the wave, we have our maximum displacement. These points we will call antinodes. We should note that if this is one full wavelength, then each...
Is that clear, guys? Okay. Okay. Now we have to know how to draw each harmonic, right? Each harmonic. Here, guys, this is called first harmonic. The first harmonic will be, or I will observe this pattern of oscillation, right? It just oscillate up and down, right? It just oscillate what? Up and down. This is what I observed. Clear? This is called first harmonic or fundamental harmonic or fundamental frequency. Here, how many nodes here? 2 nodes. Right? This one, and one antinode. Second harmonic, 1, the midpoint, 2, 3. In the second harmonic, guys, we have 3 nodes. Right? And the waves that is observed in this way. Look how will I draw these things, guys, because you will be asked to draw a standing waves. Here we have what? 3 nodes, 2 antinodes. The third harmonic will have 4 nodes. 1, 2, 3, 4, equally spaced. Right? Equally spaced. Here we have 3 antinodes. This is called second harmonic. This is called what? Third harmonic. Guys, now I want to find the wavelength. Before wavelength, this is a fundamental frequency. If I double this frequency, guys, of the generator, I will get the second harmonic. If I triple this frequency, I will get what? Third harmonic, and so on. Clear? It's called fundamental frequency. This is called what? Fundamental frequency. Any question about that, guys? Here I have to find the wavelength, guys. This is easy. How many wavelengths here in the second one, guys? Here, look to this one. How many wavelengths, guys? One wavelength, صح? Is that clear? So if this length is L, the wavelength here, guys, is equivalent to L, right? Here, the wavelength half L. Sorry, double L. I will show you why. Here, how many wavelengths here?
1.5.
Yes, 3/2L. طبعا هي راح يكون ايش؟ 2L. If I consider the first one, the first harmonic, okay, guys, عشان to show you. This is the crest, صح? If I continue the wave, this is the trough, صح? So if this distance is L, so the wavelength is 2L, صح? The complete wave is 2L. Is that clear? Okay? Guys, any question? So here we have a pattern we can follow. L lambda equals 2L. Let me write it here. Crest and trough, صح? طيب, look to this. This is what we observed. Only one crest. If I want to complete the wave, صح? So this is the complete wave. صح? This is a complete what? Wave. So wavelength equal 2L. Okay? Guys, here there's a pattern for the wavelength. Wavelength equals 2L/n, where n is the order of harmonic. First harmonic, second harmonic, third harmonic, and so on. Frequency equals n times f naught, where n also is the harmonic. The number of nodes.
طب صدق معناها ان الثيرد هارمونيك المفروض تكون 2/3L صح؟
Just a moment. Number of nodes راح يكون n+1, right? number of antinodes راح يكون n عادي. اه 2/3. انا حطيت 3/2 sorry. Yes, 2/3. طبعا اتفقنا هذا third and fourth harmonic. طيب. Define a node والantinode. We already defined these things, guys. I will define these things and I will stop here. The nodes, guys, position in the standing waves were outgoing progressive waves. Guys, eventually, initially we have outgoing and reflected progressive waves. يعني احنا أول شيء عندنا progressive waves. But when they interfere, I will not observe these progressive waves. I'll start observing what? Standing waves. And reflected wave back in opposite direction, we have to mention this. meet each other anti-phase, so they interfere destructively, and the resultant amplitude is 0. This is the explanation of the node. The anti-nodes, guys, positions in a standing waves where outgoing waves and reflected waves back in the opposite direction meet each other in phase, so they interfere constructively. في شيء اسمه constructively, sorry, right? They interfere constructively, and the resultant displacement add up, so their amplitude is maximum. Examples على standing wave systems, musical instruments with microwaves, ovens.